We will be talking about CRDTs today, of course. And yeah, let's start. So first slide of introduction, this is how you can get to me. And this is the address of my blog, as mentioned. You can see a lot of CRT materials in there, like tens of blog posts in there as well. So what we are talking today about, we will be talking specifically about rich text document, about some approach how to resolve conflicts and build collaborative rich text documents. We will be talking about Yata algorithm specifically, and we'll cover a variety of things related to it, because rich text documents are not only about sequences of characters, but also maps, formatting, moving ranges of elements and stuff like that. And about some of the real-life optimizations that we applied to the project that I'm working on together with Kevin Jans, that make this approach actually feasible for production. So if you want to try it, this is the address. It has a demo on this. There is a demo on this site. So whenever you want, you can try it, write something on there, try to break it, and hopefully give some feedback. So let's start with our problem statement. Let's say we have 3 collaborators. Each one of them has a replica of the same document on their computer. Alice, Bob, and Carol. So initial state of the document has just a single letter. At the same time, let's say concurrently, without knowing about each other's actions, Bob and Carol are trying to insert 2 different characters at the same position. They manage to do so. They are propagating their updates to other clients, other peers. And they are applying those updates on the remote peers as well. Now, there is a problem you can see there. Namely, the state of the document is not the same, right? There are different, characters are in different orders. So this is what we want to solve. We want to eventually be able to see the same state of the document after updates made by peers individually. So first approach, let's try to use a synchronization via central server. So back to square one. Carol and Bob are trying to make their updates, their inserts. Those inserts first arrive to the central server, which tries to establish some total order, usually first come, first served. Then this central server propagates the updates to all the peers in one specific order. And then those peers can apply those inserts on their local machines. Now, the problem with that, well, there are multiple problems with that. One is the latency, because now we are introducing network round trip to each of our keystrokes before we are able to display those characters on each side. Another is that if, for example, one of our peers is writing something, collaborating on this document from his laptop on the train and goes through the tunnel, we got network disconnection. And since he cannot synchronize with the central server, he can no longer insert any characters, and that's bad for user experience, right? Another issue is character interleaving, because first come, first serve approach fails if 2 people will try to insert multiple characters, entire words or sentences in the same place, basically. So what would we end up with is that we would have those words made by 2 different people mashed up together with characters interleaving with each other, which has no sense whatsoever. And final problem, we have a server, so somebody needs to maintain it, somebody is responsible for it. Well, it's also a single point of failure or single bottleneck. And it turns out that this is not an isolated problem. There are multiple issues of the similar kind that we want to solve this way. Of course, collaborative text editors, but also any kind of issue where we have a network communication that introduces some latency of variadic time span or offline periods of offline inactivity. Because if we think about this from the network perspective, there is really no difference between a very long latency and 2 peers being disconnected from each other. It's just a very, very long latency, right? So there are multiple different kinds of scenarios when the same issues are applying. So one is the cross-continental data replication. So we have replicas of the data being on the different continents, for example, or in the future maybe on the different planets. Vehicle apps, so many different kind of navigation applications, for example. Remote areas, so sensor networks, maybe we want to have some kind of data aggregations from sensor networks where those sensors exist, for example, in mine shafts or something like that. And also something that should be actually quite familiar to each one of us, when we have the single account for a single kind of application, but this application is installed on multiple devices, right? So for example, I have a Spotify that has offline playlist of tracks on my laptop and on my mobile phone, basically. And I want to, update the order of those tracks on my playlists. And I would like them to be able to connect and synchronize with each other without some kind of central server, because those two devices are perfectly capable to talk with each other without some different machine that exists, like 1,000 kilometers away. So this is also one of the use cases. And now, when it comes to establishing the order of updates, because this is basically the problem that we are trying to solve, there are two approaches. One is conflict avoidance, which is currently the most common way of solving this. So basically all of the Raft and Paxos kind of systems, like Kafka, CockroachDB, or any kind of really basically every kind of databases that you've heard about recently and probably used recently are using this approach. So we are basically relying on the cluster of network machines, usually of odd size, where the majority of nodes is deciding either on leader, who is giving us the correct order of events, or on the order of events by themselves. And the second approach is so-called conflict resolution. So basically, we are allowing the conflicts to occur, but we are providing enough metadata for each of the peers to resolve those conflicts. So assuming that we given enough metadata, those peers will be able to resolve those conflicts by themselves, because the conclusion of our ordering will always be the same. And conflict resolution is really all about maintaining the specific intent. And honestly, we as developers are very bad about preserving the intent, because most of our jobs, I think, is about taking the intent from the users, from people who are not developers, basically, and turning it into a code, right? So where this fails, basically, is when we are talking about concurrent writes, for example. So inserting characters one after another. We usually express this as insert those characters at index position 1, 2, 3, and so on. This is obvious for us. The thing is that it doesn't work when we are talking about concurrent scenarios, just as we've seen before. Same about fixing typo. We want to fix a typo in some word. So we are, for example, inserting the missing character. What if two people are doing the same thing? We are ending with another typo, right? Another thing is moving elements. So of course, move element. Just remove it from one position, insert it into another. But what if another person in the same time is trying to write something to the object that we just removed? Another thing, moving ranges of elements. So for example, we have a paragraph of text which we want to move up or down into inside of the document, while other people are still writing something inside of this paragraph. So just as I've mentioned, indexes are not very good at keeping an intent. What we need is something better, because indexes are changing their meaning over time, and since time is relative, depending on which perspective we take, which peer point of view, we have different meaning for the same index. So what we are doing, this is something called Lamport clock. So basically we are having a unique identifiers for each of our updates that we are about to provide. And this update is composable key. One is unique identifier of each peer that is ordered, can be ordered, and there is a sequence number for each of the updates made by those peers. So once peer A with identifier A makes his first insert, this insert is getting a number A1. Then next insert is A2 and A3 and so on. And important thing is that since this is a composite key, but we still can order it. So if you have A1 and A2, we can establish an order. If you have B1 and A1, we still can establish the order because peer IDs also have an order. This will be necessary later on. So our insertion inside of particular index can be changed into something like this. Now, there is a problem because there is also a mapping layer, because text editors, for example, don't work this way. They work on indexes, so we need to establish some kind of a mapping layer between the two. However, this is how this works in Yata. Basically, what we are having is we have a letter B that we want to insert. This letter, as part of insertion, gets its own unique identifier. This identifier stays the same all the time. And we are also providing left and right neighbor for these inserts. So instead of saying we are inserting something at position 1, we are saying basically we inserting something in between character identifier at position on the left side of this place that we want to insert and on the right side that we want to insert. This way we are building our update basically. How does this help us with conflict resolution? So let's say that we have some initial state of the document. This is about blocks. We are calling them blocks in wires, but this is not a talk about blockchain technologies, and so don't worry. Those are just blocks, and blocks are representing a single insert made by a person or a couple of sequenced inserts. So if a person is writing down several characters one after another, this also can be as a single block, basically. If somebody is copy-pasting text, this could also be a single insert. So this is basically the idea. And on the top, you can see the current state of the document, which is basically A and D. This is our string. And we want to insert something. The thing is that we have two peers trying to insert different letters at the same position. And those inserts are basically what we were providing in the method signature before. So one peer, B, created an insert B2. Another peer created an insert A2. And those inserts are supposed to be inserted, those updates are supposed to be inserted in between the same range of neighbors, basically. So first, we see that we can, at least without any conflicts, insert one of them. So let's start with A2. Once you want to start B2 now, there is a problem because B2 is supposed to be inserted between A1 and B1. And the thing is that there is already an existing block in between. So we have two possible places where this element is supposed to be inserted. And the thing is that no matter which was the order of the operations, if A2 or B2 were supposed to be inserted first, the order should stay the same, always, no matter at the in which order they were applied on which client. So we have two possible places. And what are we going to do? Well, this is where we are using those IDs, those block identifiers. We are going to order conflicting updates in the order of their identifiers. In this case, we assume that B2 is greater than A2, and we order them in this specific order. So if we would change the order of application of updates now, so if B2 would be inserted first and conflict would occur on A2, the thing is exactly the same. We are ordering A2 as something that is less than B2, so we will insert it before B2. And this is how this algorithm basically works. And we were talking about sequences, but it's not only about sequences. The same approach can be used for maps, for example. And let's say that we have a map with key value entries. And basically, key is our some kind of string for identifier, and the value can be anything really. The thing is that we can think about inserting to the value under a specified key as it was pushing element onto the end of the list. And this is what we are going to do. So we are basically creating a new block, provided a new identifier, say it is supposed to be inserted on the right-hand side of the A1, which was already known to us. And we will be basically repointing the pointer of that entry onto the last inserted block. And then for optimization reasons, we are going to delete, in this case, it's just a soft tombstone, of all elements that were occurring before. So those tombstones can be optimized later on. But this is basically the idea. Updating the element of the map is no different than inserting something at the end of the list in this sense. We can use, and since we already covered the thing about config resolution, the config resolution works the same way. It's the same algorithm. What is novel, and this is actually the first time we will be talking about this in public, it's about moving elements, because just as we covered, moving elements, especially ranges of elements, is different than removing element from one position and inserting it on the other, because we lose the causality of operations that could happen concurrently over this moved element. So Martin Kleppmann made a proposition about moving a single element node inside of the recursive document tree. What we will be covering here is moving ranges of elements, and this is something that we have been working for this entire year, basically, since June, I think. Yeah, since January, I think. Yeah. So going back to our first document state, this is the exactly first document state that when we had resolved our conflict, right? Now, what we want to do is to move range of elements from index 1 to index 2, inclusive on both sides, into the position of index 0. So if we would like to draw a diagram, this is what it would look like, right? So we are going to encode this way. We are creating a new block of different type, which describe this move operation. And since we don't trust indexes because they are changing, we are changing those indexes onto the block IDs. So we are creating a new block with new ID. We are saying that this block is about to move a continuous range of blocks starting from A2 to B2. And since it's about to be inserted at position 0, we just need to say it's about to be inserted before current block at position 0, so before A1. And that's all. The only problem is that this introduces a kind of indirection when you want to read it, right? Oh, sorry. There's one more thing. We are marking the blocks that we moved with new kind of field, informing that they were moved by some other kind of operation. This will be necessary when we are about to read them. So yeah, we need to read that now. So the thing is that we create some kind of iterator that points at the beginning of our collection, right? We are going over the first block. We see that this first block is of move kind, of move type. So we are introducing something that is called move stack, and this is a very similar thing on how the function call stacks work in the programming languages in the virtual machines, basically. So we are building something that is called move frame, just like activation frame when we are doing method calls. And we are saying this move stack points to the block A3. This is our origin. And it covers range of blocks from A2 to B2, just like this move element. So now we are jumping to the first block from that range, which is A2. Iterates our iterator over it, read B, because this was the content of that block. Then go to the next block on the right, take C. Then go to the next block, and we are seeing that we reach the end of our range from the current move frame. So once we reach the end, we are removing this move frame, going back to the origin point, just like basically just like in function return address, and then we can move onward. So we are going to read A. Then our iterator goes again after those blocks that it already visited. And this is where we are using this moved field. So we are seeing that this block has been moved by A3. So we are comparing it against our move stack, and we see that on the move stack, there is nothing. Actually, if there would be a different move frame of different type, it would also mean the same thing. So we can just skip over it and over the next element as well, over the next block as well, because it also has been moved already. Then we reach the last block, and we can reach the D. The reason why we needed that move stack was because if we are moving ranges of elements, those ranges can also contain move operations. So move operations can be nested recursively. And we need to take that into account. So, optimizations. Yeah. First, we need to know our environment. Because CRDTs are very popular in like two kinds of systems. One is peer-to-peer collaboration. Second one is client-server. Peer-to-peer, wires, YJS, so the thing that I'm working on. Auto-merge, which is our direct competition, I would say. On the server side, ReactDB, Amazon DynamoDB, AntidoteDB, those are popular choices. There are like different approaches that, well, different things that we need to measure, because for example, inserting number of operations per second is not actually very great to compare when we are talking about peer-to-peer applications, because those operations are strictly related to number of actions made by the user. What is more important is, for example, how many updates are we capable of doing, because update is basically this thing that is already computed, right? So all of the user indexes are already mapped to the block IDs and stuff like that. So those are two different things, really. The same is about bandwidth type, about size of the updates, about how big the actual document is in memory, because if we can store the entire document into the memory, then it simplifies a lot. So one of the things that we need to introduce is basically about reducing the number of operations, because imagine we are about to copy-paste the entire page of the text. If we described only semantics for inserting a single characters, this means that we are now pasting few thousand characters as a separate operations. We could do it as one, and as I said, this is what we done in YJS. So how do we do that? If we took a look at these two blocks, okay. So going back to the topic, if we look at these two blocks, if you are, experienced enough in this notion, you can see that person A inserted character A, then character B right afterwards in a sequential manner. So honestly, this means that somebody just did two keystrokes without anyone else interfering him. So basically, this means that we could represent those two blocks as this single block, which has a value of identifier of A1. It stores two characters instead of one. And now this block is responsible not for one update, but for the two updates, A1 and A2. And we can infer that from the length of the elements that it's being stored inside of this inside of this block. Now, those two blocks have different in-memory representation, but the logical representation is exactly the same. And this means that if we can squeeze those blocks, we are calling this squashing, like in Git actually. If we can represent multiple operations as a single block, it means that our copy-paste operation can also be, for example, represented as a single block. If we want to insert some new kind of operation right now, we need to take into account that the last block is representing more than one operation. So its identifier is basically identifier of the last block plus the length of that block. So this is how it works. And again, here, it also can be squeezed as well. It also can be squashed. Wait a second. So yeah, since we gone over squashing, we also need to be aware about splitting. Because if somebody has pasted a page of the text and somebody else wants to write something inside of it, we need to do something because our block representation will not hold on any longer. So what we are doing, for example, here is this type of fixing stuff. So we need to insert a letter inside of existing block. What we are going to do? First, we are splitting this block in two, because as we said from before, 2 blocks and 1 block can have different memory layout, but the representation in the logical sense stays the same. So we are doing that exactly. We are reversing our squash operation from before. And now, all we need to do is to insert this new block in between. Now we cannot squash those blocks that we just split anymore, but this is how it is. Sorry, this is a demonstration of life. So this is how it works. And you can see here that, for example, A4 has a left origin set on A3, just as A5. And the reason for that is that those identifiers are identifiers of the neighbors at the moment when we inserted them, not as they are at the present moment. And we need this immutable representation at the moment of insertion because this is used for conflict resolution. And just like we don't like mutable indexes, we don't want to mutate those origins, left and right neighbor. So another thing is about block insertion time, because ideally, even if you are not working on the persistent memory, but on the RAM or whatever, inserting something at the end of the collection is still usually faster. Well, if we are talking about arrays, for example, it's still usually faster than trying to split existing collection and put something in between, at least for arrays. So we want to maintain this, this speed of operations. And to do that, I was presenting those blocks the same way that we are about to read them, right? So those blocks were nested next after another. And this is useful for reading, for users, or for people who want to understand how this algorithm works, but this has nothing to do in how this is implemented under the hood. So what we have under the hood is basically, we are calling this a block store, and block store is basically a hash map of each peer ID that we ever got, whoever had written something to our document, and a list of operations submitted by this user, or by this agent, actually, because this same user can have multiple peer IDs. Now, this representation is very useful for us for 2 things. One, if we want to figure out what is the ID of the next block, we can just see what was the last ID that we have covered in our block store. So taking the last block, take its ID, add a length of elements. If we want to find some block given its ID, this is also very easy because all we need to do is to pick up the collect client block list and do a binary search over it. And it's even better if we are propagating the updates. Namely, we have 2 users. As you can see, Bob is missing some of the updates that Alice have, namely A2, A3. How are we going to synchronize that? We don't want to synchronize entire document content. So what are we going to do? Well, Bob creates something that is called vector clock. Vector clock basically tells us about the state, the most recent state of the Bob's document store, his block store, his document. And basically A2, B3, C4 means those are IDs of the blocks that I haven't seen and haven't seen anything after them. We are encoding this vector clock, send it to Alice basically. She can compare it against her own vector clock, and she sees that she has actually some of the new updates that happened after this vector clock information. Now she can encode just those 2 updates, and we have a very domain-dependent way of encoding those updates. I mean, the footprint is much smaller than protobuf, than Avro, or any kind of binary encoding that you can think of, basically because it takes into the account our knowledge about the domain. So for example, we are not encoding the block IDs at all. We just need to encode the first ID of the block in the sequence and then compute those IDs when we are going to decode the stuff. So those block updates have very compact representation. And this is also possible because of this layout that I'm presenting here. So going back, we are producing the update that contains those missing blocks and propagating them onward, right? So we don't need to put more data than it is necessary for us to do. And now, this is the last one I want to talk about. This is the Rust code, because the thing that I'm actually working on is the Rust port of Vue.js, which is called wires, written YRS, but we are calling it wires. So it is basically because we want to support cross-platform for all of this stuff. And it's binary compatible with Vue.js. So you can have browsers with Vue.js on board. And for example, Python servers, Ruby servers, or anything that, as long as you want to write a binding in your language to do so, and write and propagate those updates on the server side as well. And yeah, this is the Rust code. And the idea here is all about really inserting a few pieces of text one after another. The problem is that this is what user sees, but translating between those indexes and those block IDs can take a while, right? And this is why, for example, wires doesn't have a great history about the number of operations made by users, because we don't care. I can still do something like 5, maybe 30,000 of operations per second. If you can keystroke faster than that, then yeah, let me know. What matters for us is the number of updates that we want to integrate from other peers, because as multiple peers are inserting, their own keystrokes, the number of updates and the speed of the volume of those updates is related to the number of peers, not to the capabilities of a single person. So this is what we want to optimize for, and this is what previous section was about. However, there are still people that have problems with that. So the idea here is that we want to introduce something like called cursors. So basically, those are equivalents for the cursors that you can see in the text editors. So basically, you start from specifying the index for the cursor. This is our lookup. This cursor that you get returned basically remembers the left and right neighbors for this position that you've picked. And once you have this cursor, basically any kind of operation that is done over arrays or text can be represented, can be called within the context of this particular cursor. And this is how it is going to be implemented within. So if you want to insert, for example, some piece of the text, you can do it through cursor. Then our cursor inserts that text because it maintains the information about the neighbors, and it's advanced by the length of the newly inserted blocks. And we can do it on, and hopefully you will be able to see this API open very soon, because we are still working over that. And those cursors, in Vue.js, this is called search markers, and they are basically cached inside of the document structure. In wires, they don't exist yet, but we want to provide them in this way. So every people could be able to marry those cursor representation with their own editor bindings, basically. So yeah, this is it. In summary, we've gone through how Yata works, what was the problem that we wanted to solve, how to solve it using Yata algorithm, how to introduce the not only sequence resolution but also map inserts as well, move operations, which is totally novel. You won't see move range operations in probably any kind of other library right now. And hopefully soon I will describe this in more detail on my blog. And yeah, a little bit about optimizations. Now, there are several projects if you are interested in this CRT area and you want to maybe not contribute to, because not all of them are open source, namely DitoLife, I think it's closed source. But if you want to, you can try it. And if you are interested in more about this entire topic of CRDTs, because we just scratched the surface really, then CRDTs Deep Dive is my series of, I think, 14 or something blog posts about CRDTs, and they contain code snippets that you can go through as part of the tutorials if you are interested in different ways of doing the same thing around, basically. And there's also a website called crdt.tech, which is basically an aggregator website about those. And something that I would like to highlight is also a blog post made by Seth Gentle, which talks about how to make CRDTs even faster and his experiments on that field as well. And what was wrong with existing CRDT implementation, why were they considered slowly for so many years. So, thank you.
Thank you, Bartek. Do we have any online questions? No online questions.
Hi, thank you very much for the talk. I have a couple of questions. One is like the algorithm that you describe for representing lists is a replicated growing array. Is it that's a question? And also, if I understand that you also can represent maps, so that means representing trees. Is it like how does this representation of tree structures work? Is it like an RGA of RGAs could be?
Yeah, so basically the question is about recursively nesting different kind of CRDTs into each other, right? Into a tree structure of documents. So the answer is yes, because here we only explained actually three kinds of blocks. One is about string insertion, second one was about deleted elements, third one was about move operation. But in practice, there is something, in YJS we have things called maps, arrays, text, and XML as well, which represent collaborative XML structures. And the idea is that if you are, for example, inserting a Y map into the Y array at some index, this Y map is being wrapped as another kind of block of specific type that maintains this information. So you can create a recursively nested documents of any kind you like, really, as long as you remember the schema that you are using, of course. So it is possible to insert those collaborative types into each other.
All right. And so it's like the algorithm is a replicated growing array, or is another algorithm?
No, it is exactly the same algorithm, and this is actually why we wanted to maintain Yata algorithm for maps, because what we are caring about during the replication and config resolution process is not about the type that we are working on. It's all solved using Yata algorithm over the blocks of particular updates. And the nice thing is that, for example, you can on one side write something as a text, for example, and you can project it onto the array if you want. And then you will be able to read basically an array of characters for that piece of text. So it's all the blocks all the way down. And if you have something to do with maps or arrays, it's just your interpretation of what those blocks means.
All right. Thank you.
I have a question related to a sentence that you mentioned during the talk, that when you inserted a block between two blocks during splitting, and you mentioned that these blocks can never be merged again. I was wondering whether there is any snapshotting in Yata. So for example, after a while, the participants could try to make a snapshot and merge all the blocks into a single block.
No, this doesn't happen, because if we are working on client peer-to-peer applications, basically, you never know if there is some kind of third party that have edited your document, and they just didn't connect to you for like a year or several years, and you didn't knew about this, right? But when they do, we still want to be able to merge with them. And this is the problem. So it's not like we can snapshot in a single point in time. There is approach called pure operation-based CRDTs that allows you to snapshot things, but they assume that you know how many peers, how many members are sharing the same data. And this is why it's mostly useful for server side, because then we have control over it. But it's not this scenario. We are not writing something for servers. This is something written for the clients. And if you are worried about the footprint of that, honestly, we have something that is called stack editing trace. It's basically a Martin Klefman, who is one of the leading guys on this field, basically made his PhD thesis, and he recorded entire writing process in the sense of updates and changing the cursor position and stuff like that. So this is basically the history of him writing his thesis, and it takes around 150 kilobytes or something like that when it's in compressed form. I don't remember how much it takes in memory, but in our benchmarks, we applied the same update, same stack editing traits 100 times, and we haven't reached the end of the operating system memory. So I guess you probably won't reach it as well if you are using it for the cases that it's supposed to be used, like documents made for several collaborators.
Thank you.
All right, I'm afraid time's up. Thank you, Bartek.
Thanks.